The reason why this section of this class is so difficult is because it's a lot of old school stuff. Many of you, probably all of you, lost your power over the week, right?
Is this related to?
Even though you lost your power, and let's say you didn't have a calculator with batteries in it, you are expected to still be able to graph a polynomial by hand. That's our goal here. So if I were to give you a polynomial like x to the 6 plus 3x cubed plus 4x squared minus 1, you can still, using some strategies we're going to learn for the next week, graph that by hand. By hand. And luckily we do have technology, so we have a couple of cheats here and there. First thing is to identify x-intercepts with our polynomial. So can somebody please identify at least one of the x-intercepts here?
-2.
Close.
1.
Close.
X-intercepts?
X-intercepts, I'm going to give you a hint, it's a coordinate.
A coordinate.
So,
-2, 0.
very good. -2, 0
Oh.
is one of my x-intercepts. What's another one?
1, 0.
1, 0.
Is that 1?
Yeah, it's 1.
That's the one, yeah. And the other one?
3, 0.
3, 0. So this polynomial has 3 x-intercepts. Now we're going to also call these zeros because we want to be able to solve for the polynomials. What good is looking at the x-intercepts if you don't have a graphing calculator? Well, you'll have to find the zeros and then turn those into x-intercepts if you're going to do this by hand. And my zeros, that's what you're alluding to when you said -2, 1, and 3. Those are numerical values. So notice the difference between x-intercepts, which are coordinates, and zeros, which are actual values. But these will be interchangeable. If I say zeros, I mean graphically x-intercepts. We saw this when we talked about quadratics. Now, another aspect or characteristics of a polynomial in this graph is end behavior. What is my graph doing on its ends? On the left side, where's it going? On the right side of my graph, where is it going? There is actually a trend, and that is if your graph is an even function, so like y equals x squared, notice my power is an even number, both sides are going to go up towards positive infinity. That always happens. Doesn't matter if I have x to the 4th, x to the 16th, an even power is always going to go up on both sides. Now, if I were to put a negative in front, like y equals -x squared, well then that reflects the graph, and both sides will be going down. So that's always the case with the negative. Like, let's say -x to the 12th. This graph will be going down. Now, I am talking about the highest power. So I can add a x to the 16th plus, let's say, x to the 5th. 16 is larger than a 5, so this is my dominant power, which means this graph will still be going up in both directions. And even numbers. Both ends are doing the same thing. They're both even, right? Now with odd powers, so if we look at our cubic function, y equals x cubed, where 3 is an odd number, it's going to follow this trend, where the left side is going to go down towards negative infinity, and the right side, facing me anyway, is going to go up towards positive infinity. So it's always going to look like that. No matter if it's x cubed, or x to the 5th, or x to the 17th, it's always going to have this kind of end behavior. And if I slap a negative in front, well then it flips. The left side is going to go up towards positive infinity, and the right side is going to go down towards negative infinity.
So you can think of it like this: positive goes in what do you call it? Positive slope, and then negative going in negative slope. See, look like this.
I see that. That's the first time I saw it. So exactly what he was saying, like this, right? If I were to connect it like that, that's a positive slope. If I connect this one like this, that's a negative slope. You know what? I've never noticed that before. That's exactly what's going on. Yes. Very nice. Okay. So, notice we were talking about odd functions here, odd numbers, where my highest power is an odd number. So this is what they had to use back in the day. They used kind of a table like this, where they looked to see, okay, what was my end behavior? Is my polynomial an even or odd? And then here's how the ends would dictate. So first we saw how to graph, once we find the zeros, which we're going to do for the rest of the week, my x-intercepts. Now I'm going to take the end of my x-intercepts. I know my graph, how it's going to end, so I'm going to draw the end of it. And we connect it by looking at the other part, which is intervals of increasing or decreasing, and turning points. Now, I don't want you to get confused. In behavior, we're talking really about the range. Notice it's going up in terms of y. Both going up here, both going down. This arrow is going down towards negative infinity, this arrow is going up towards positive infinity. When we're talking about intervals, we are more focused on looking at a domain. Wasn't touching it. Domain. And when we read the domain of a function, we are reading it from left to right. So even though I see my arrow going down, this is actually referring to the end behavior and not what we're going to talk about now, which is the intervals of increasing or decreasing. So with the domain, we're always going to start at the lowest or the smallest value first, which is down here at negative infinity. And I'm going to trace my graph from left to right. So as I'm drawing my graph, what is my finger doing? Yeah, it's going up, or it's increasing. Again, this arrow coming down is referring to the end behavior. But as far as intervals, it is increasing. Then I hit what's called a turning point. And it's called a turning point because I'm no longer increasing. Now what is my finger doing?
Decreasing.
It is decreasing. And I hit another turning point, which means I'm now no longer decreasing. I am what?
Increasing.
I am increasing. So my graph is going up.
I
So that-
could say there's so much more to that, but what if there was no turning point? That's what I'm trying to figure out.
Oh, we'll talk about that. So it follows your finger as you're tracing your graph from left to right. I am increasing. I hit a turning point. Now I'm decreasing. Hit another turning point. Now I'm increasing. With these turning points, we have a high turning point here, which kind of looks like the top of a mountain. That is called a maximum turning point. Then I come down here and I hit a low point, so kind of like the valley. That is a minimum turning point. And turning points come from when you change intervals, from increasing and decreasing, or from decreasing and increasing, or from increasing to decreasing. You're switching. So if I were to label these intervals, they're going to be labeled in terms of the turning points here. So these will separate my graph's intervals. So I see I have 1, 2, 3 intervals. This interval here where I'm increasing, I'm going from negative infinity to this turning point, which is negative 2. Right? I'm increasing from negative infinity, stop here at my turning point at negative 2. And then this interval where I'm decreasing is going from that negative 2 turning point all the way to positive 2. And then from here, from 2 all the way to positive infinity, I'm increasing again. So there are my 3 intervals and how they're separated between my increasing and decreasing. Note again, we are talking about the domain. So if I take all of my intervals and put them together, you should get the domain of the graph. Is this graph not going from negative infinity all the way to positive infinity? It is. That is my domain. The intervals just separate your domain between the increasing and decreasing parts. So as you look here, if I ask, what is my end behavior? What is my graph doing at the ends?
Decreasing.
Yes, on both of these, they're going down, right? Towards negative infinity. This is my end behavior.
Oh, you said end. I thought you said end at the beginning. Like end.
My end behavior. Now, as far as my intervals, how many turning points does this graph have? Very good. It just has one right here. Between this turning point, as I start from left to right, what is my finger doing as I'm tracing it?
Increasing.
It's increasing,
Decreasing.
and then it's decreasing. Yep. So notice the difference between int behavior, where it's both going down, and intervals of increasing and decreasing. One, you just look at the ends. What are they doing? The other, you're tracing it from left to right. What is your finger doing? Now let me give you a moment to try to figure out the intervals of this polynomial while I take a test. So when I separate this out into its intervals, I want to figure out where is it increasing and where is it decreasing.
Ooh.
First up, can somebody tell me how many turning points does this polynomial have?
3.
3.
That's what I was
I have 1, 2, and 3.
3 turning points.
How many maximum turning points?
Maximum?
2.
3. Wait, 1?
I just have one hill, right?
Yeah.
One mountaintop.
Mm-hmm.
How many minimum?
2.
I have 2 valleys. Yep. So I have a total of 3. Now, I have those here, here, and here, which means it separates my polynomial into how many intervals?
4.
Very good. So I draw my line here. I see it is 1, 2, 3, 4 intervals of increasing or decreasing.
Well, you said 1, 2. I can't see. 1, 2, 3.
The lines.
The lines. So I have an interval here,
Right, that one.
interval here, interval here, and interval here. My 3 turning points separates it into 4. So I'm starting from left to right, or what's the end behavior?
It's increasing.
Decreasing.
Well, no, the end behavior.
Oh.
It's like at the top.
The left side is doing what?
Increasing.
It's going up.
Mhm.
You wouldn't say increasing with end behavior. You would say towards positive infinity or going up.
Okay.
What's the right side going?
Going with the positive thing.
Going up or positive infinity. Okay, now let's look at intervals. So as I start here, I'm starting from negative infinity to this turning point of 1. What is my graph doing? It is decreasing, yep. So decreasing. So what is that interval between negative infinity and 1? Now I hit a turning point at 1, and it is doing what?
Increasing.
It is increasing. Here, between 1 and 3. I hit another turning point, and I'm now doing what?
Decreasing a little.
Yeah, decreasing a little bit. That is between 3 and 4. And then I hit one more turning point, and now I change to increasing. Between 4 and where?
Positive infinity.
Positive infinity. Yep.
Yes, sir.
So that tells me that this graph's domain is going from negative infinity to positive infinity. And it is. Let me 1 and 3.
What do you call that?
And that is, we'll just call it D, or decrease. All right, so there's my 4 intervals. And it's separated between its increasing and decreasing. Now, speaking of turning points, there is a little rule and trick that we can find out how many turning points a polynomial could have. And it goes like this. Polynomial functions of a degree n, so my highest power, we're calling n, has at most n minus 1 turning points. So take the highest power and subtract 1. That tells you how many turning points it could have at most. Could have less than that, could have none, but at most it's going to have n minus 1. So if I look at x cubed plus 4x squared plus x minus 4, degree 3, my highest power, has at most 2 turning points. 3 minus 1 is 2. And if I look at that red graph here, I see it does have 2 turning points, don't it?
Amazing.
Increase, turning point, decrease, turning point, increasing again. Now remember, at most, if we actually look at the parent function, x cubed, in its most basic form, Do I have any turning points? Don't think of it as a road you're driving down. Think, did my finger ever change from increasing?
No, we just kept increasing.
Yes, it kept increasing. So what you would say is, I have no intervals of decreasing, and from increasing, I'm going from negative infinity to positive infinity. So there are no turning points
And
here.
that red one went from, that thing went crazy.
Yeah, the red one has 2 turning points, so it's increasing, decreasing, and then increasing. So here's the same type of function, x cubed, where that's my highest power. It could have 2 turning points, it could have no turning points. And I can't think of how you could set it to where it could have 1. Usually the turning points come in pairs. At least with the functions. So look at here, x5 minus 2x squared plus 1. At most, I can have how many turning points?
4.
4, right? Well, how did you get 4? I saw my highest power, which is 5. Took 5, and I subtracted 1. 4. What about x squared plus 1? How many turning points could that polynomial have?
1.
It can have at most 1. So you look at its highest power 2. Take 2, subtract 1. That gives you 1. Next, I could have how many turning points?
8.
8. So 9 minus 1 is 8. And then last but not least, x12 minus 3x squared plus 7. How many turning points?
11. 11.
It could have 11. Yep. It could have up to 11. Now, hypothetically, if I were to change this to a 22, how many turning points would it have? Would it still have 11?
No, you have 21.
I have 21. So again, don't assume that it's written in standard form. Don't just keep on going off the first term here. Look through the polynomial. Figure out what's the highest power. Subtract 1 from that. Get into the habit, because in the highest power of polynomial is very important, especially moving forward after today. So let's actually look at the turning points from these graphs. The first one, the red graph, you told me it could have 4. As I look at it, how many does it actually have? The graph in the red. How many turning points? 2. It could have 4, but in this case, with the way these other values in the middle are laid out, it only has 2. The second one, x squared plus 1, you told me it can only have 1 turning point, and how many does it actually have?
1.
Yep, looks like it only has 1. And then the green graph, you told me it could have 8. How many does the green polynomial have? 0, right?
Settle.
0. My graph is always increasing. There's no turning point to where it decreases. And then last but not least, x12 could have 11. How many does it actually have?
3.
It actually has 3. Very good. So there's our characteristics. Turning points, we can now graph those by just taking my value in and subtracting 1. Intervals of increasing and decreasing. In behavior, and x-intercepts. That's all we need to know in order to sketch a polynomial.